All right. I feel the discussion again here, and we'll continue throughout the week. Thanks.
So a couple of things before I start my talk. First is it's a great pleasure to be here, and thank you for the opportunity. And the second thing is I, along with my co-authors, are economists by training, so there are at least two implications of that. One is that I don't know many of you, and so I look forward to meeting you over the next couple of days. And the second is that when I look at the slides of the previous talks, I realize that my talk is a little too, very much less illustrative than your talks, with almost no graphics. And so apologies in advance for that. In this paper is joint work with Ron Aylett and Kafir Elias. So Ron is at Ben Gurion University and Kafir is at Tel Aviv. And in this paper, what we want to do is to introduce and study a Bayesian measure of privacy loss. A lot of you have worked on differential privacy, and you know that it's a prior free notion. So just as a quick reminder, differential privacy requires that the realized outcome of a mechanism does not reveal much about any individual participant's type. Okay? But we think that this is mostly from an outsider's perspective, and I'll explain what that means. So if you think about a mechanism that satisfies this formal constraint of differential privacy, and when you go to implement it, you still need to collect people's types and then map it to the outcome. But what if we worry that the person collecting the types, or the designer, is not benevolent enough? What if we worry that he or she might, in this case, know too much about the agent's information? So what we want to do in this paper is to study mechanism design under a different Bayesian version of privacy constraint that limits how much information the principal can get from the agents through observing what they do in the mechanism. Okay. So to give you a little more details, we're going to measure the privacy loss by how much the principal learns by observing the agent's choices in the mechanism. As when I said it's Bayesian, our principal is going to start with some prior belief, F, about the agent types. He's going to offer a general mechanism, which is potentially indirect, and almost because of the privacy constraint, it's going to be indirect. And this mechanism is going to specify a set of messages that the agents can send, as well as how these messages are mapped to the outcome. Okay, so all of this is standard. And then the agents, given the rules of the mechanism, will send messages and play an equilibrium. Now, the place where we depart is to observe that given what these agents send in the equilibrium, the principal can form a new belief about the agent's types. So the principal can Bayesian update and get information about how the agent types are distributed. So we're going to define the privacy loss as the expected distance between the posterior and prior beliefs as measured by KL divergence. Okay, and the expectation here is over the messages that are sent in equilibrium. So the exercise that we're going to do in this paper, yes?
A message sent by a random agent drawn from F or by an arbitrary agent?
So that's a great question. Actually, I'll maybe after the next slide, the answer will be clear. The principle, so the exercise in the paper is to assume that there is an exogenous constraint on how much privacy, how much information can be communicated through the mechanism. And under this constraint, we're going to solve for the optimal mechanism. Okay. So let me offer a couple of discussion which will in particular answer your question. So the first point to note is that this definition turns out to be equivalent to the mutual information between the types and the messages. And there's an earlier paper by Xiao, who, in the earlier version of the paper, considers this mutual information measure. But what he does is to impose this as a cost to each agent. Instead, what we do is to take the viewpoint of a regulator who's going to exogenously impose this constraint. And so by doing that, we're now going to explicitly model the agent preferences for privacy. But alternatively, if you wish, you can also interpret our model as saying that each agent would like to participate in the mechanism if and only if this constraint is satisfied. But that would assume that agents all have the same preference for privacy, and it takes this particular threshold form. Okay. The second point that I want to note is that in this measure of privacy that I defined on the previous slide, the measure basically takes the average across different messages. You can think of a more stringent notion, which we call the ex post notion, that requires that regardless of what message is sent in the equilibrium, the principal's information gain does not exceed this threshold.
So you make sure we understand what is the averaging that's happening here?
Yes, so let me go to the previous slide. For each realized message M, there's going to be a posterior belief, and you can calculate the KL divergence. But these messages are sent by different types according to their equilibrium strategies. So the expectation is over the messages with probability given by the equilibrium strategies. So going back to what I was saying, a more stringent notion is to require for all messages, the information gain does not exceed a certain threshold. But as we show in the paper, the results for both cases are going to be similar. And in this talk, I'm just going to focus on the ex-ante case where we take the average.
Isn't your ex post notion equivalent to differential privacy?
That's KL divergence.
No, but it requires like worst case ex post.
Yes, so in the worst case sense, it is. But the measure by KL divergence is different from differential privacy. Right, because in differential privacy, you don't have a prior to begin with. Even in the ex post notion that we're considering, we're saying that given your prior, how much additional information you gain from the mechanism, and we put a bound on that. So assuming that the prior is already very precise, then this kind of constraint would not have much bite.
I have a question about this, actually related to that. So if you think of this as a constraint that someone's going to verify, somehow the prior has to be specified as part of the verification process. And we have to agree that that's like a good prior or the right prior. Like, how do you, like, if I'm whatever company that's trying to justify my mechanism to a regulator, and I say, oh, my prior is uniform because I know nothing, and they kind of sign off, but that's actually, I actually have lots of other information on the side. Like, how does that play into?
Yeah, so I think that's a great question. In fact, that's something I'm going to briefly touch on in the conclusion slide, but I'm glad you brought it up already. So there is indeed an issue of when actually implementing this, the regulator has to perhaps solicit the prior from the principal, and the principal may have an incentive to lie. So you can imagine a bigger problem where the regulator would take into account that strategic incentive and impose constraints that would at least minimize the cost of that. We haven't yet done that, but I think that's definitely a worthwhile direction to pursue. Okay, and then finally, there's this issue of how we aggregate the privacy measure across different agents, whether we take the sum or we take the worst case. In the paper so far, we are focusing on application with only one agent. So for this talk, at least, we will not worry about that. Okay, so let me let me talk about the specific application, which is basically the screening model of Musa and Rosen. So in this model, a seller is going to sell an object to a buyer at some quantity or quality level Q. Okay. And the buyer in turn is going to pay a certain amount P to the seller. The buyer type we assume is distributed according to this prior distribution F. And then once the mechanism determines the price and the quantity, the profit is going to be realized, and then the buyer is going to get quasi-linear utility from this allocation. Now we're going to make a simplifying assumption that the prior distribution F is such that the virtual value is increasing and positive, so that in the classic model, we would have different types get different quantities, and higher types would get higher quantities. Okay, and everybody is getting positive amounts. Now, the difference in our model is that the seller has to maximize profit subject to the aforementioned privacy constraints. And so so that's how we write down the constraint optimization program. Again, here we're considering a general mechanism where the messages may not be the types themselves.
Sorry, are you assuming that all virtual values are positive?
Yes. So the lowest type wouldn't be 0 in particular.
All Meyerson virtual values are positive? That's what you mean?
Yes. So theta minus 1 minus f capital F theta divided by the density.
So the reserve price to set would be 0 then? Is that what you're saying?
Can you say it again?
That would imply that the reserve price to set is 0 if all virtual values are positive.
Well, I'm not sure I understand what you mean by the reserve.
The reserve price is the virtual value that crosses from negative to positive.
Mm-hmm. Yep.
And so if they're all positive, then
Yeah.
the reserve price would be...
Yes. So the reserve price would be, so you wouldn't set a reserve price. So as I said, the standard model would predict the seller would sell to everybody, wouldn't exclude anybody by using a reserve price.
Can you explain the Q squared?
Oh yeah, so that's just a simple. So in the paper we can do arbitrary cost functions, but for the talk I'm just going to focus on a quadratic cost function. So any convex function can be accommodated. So basically it means that producing higher, the marginal cost of producing additional quantity is increasing.
So that's the monopolist production cost function?
Yes. Yes. Okay. So the first main result we show is that, well, given any finite capacity constraint, there exists a optimal constraint mechanism where the message space is just an interval partition of the set of all types. And in equilibrium, each type is going to report the interval to which it belongs. Now, we also show some further properties of the mechanism. For example, the constraint is always going to bind in any optimal mechanism. And furthermore, if the privacy constraint is very tight, then it's optimal to use exactly 2 intervals. So let me give some intuition for why intervals emerge in our model. First note that there have been some papers that explicitly impose an upper bound on the number of messages that can be sent in the mechanism. And in this way, they're able to derive the optimality of intervals. For us, the argument goes a little differently. The first thing we do is to show that we can remove redundant messages in the following sense. So first of all, if 2 messages lead to the same quantity, then without loss, we can assume that they also lead to the same price, because the one with the higher price will never be selected. And secondly, we show that they can't even lead to the same quantity in the optimum, because if they do, then the principal can combine them into a single message without affecting the outcome of the mechanism. But what that would do is to average the posterior beliefs from the original two messages into a single posterior belief. And because the cost function on privacy is convex, such an average saves on the privacy measure. So in this way, we can argue that different messages are going to be mapped into different quantities and different prices, so they can be ranked. And then, following from that, different types that send different messages are going to partition the type space. And finally, we argue that each of these partitions is convex, and so they must be intervals. And as you can see, this part of the argument does not quite rely on the specific form of KL divergence. In fact, any cost function that is convex in the posterior beliefs will do the job. However, where we do use the KL divergence is to show that in the optimal mechanism, there are only finitely many intervals. And the technical issue is that basically the space of partitions is not compact. So we cannot choose a subsequence of partitions and find the limit point, etc., etc. What we have to argue is that compactness can be restored by showing that among all the intervals the principal offers, there can be at most one that is very short. And so that in turn will put an upper bound on the number of intervals used. The reason there can be at most one short interval is that if there are more than one, then they can be merged, and it will save enough privacy to enable a profit gain by dividing another interval that's relatively long. So the intuition here is that the log term, so recall that in the KL divergence, there is a log term, and that log term punishes very heavily against precise information, even about a small set of types. So that's the fundamental reason why there can be at most one short interval. Now, in general, it is a little hard to pinpoint where the cutoffs of these intervals lie. But we can at least do that for the uniform distribution. So assume that the prior of Bayer types is uniform. Then we get a key simplification that the ordering of these intervals in the mechanism does not affect the profit or the privacy measure. And because of that, we can simply focus on the length of these intervals. So the characterization we get is that for the uniform prior, the optimal mechanism is going to partition the type space into all but one long intervals, which are equally long, and one shorter interval, such that the privacy constraint is exhausted.
So just to make sure I didn't lose too much, are we considering a case with many buyers and
just one person?
Just one buyer, one seller?
Yes, just one buyer, one seller. But if you think about the previous result on intervals, the same argument extends to an auction setting.
But so the expectation again is also over the type of the person, the distribution over types.
Yes.
So like if I show up and I'm of a particular type, maybe my privacy would be violated a lot, but only rarely in distribution.
Yes, but if you prefer, you can use the ex post notion. As I said, the results would be similar. Yeah.
Sorry, I think I'm confused about something really basic. So we're trying to maximize revenue or
Yep.
profit subject to privacy constraints.
Yes.
from some distribution such that the original thing that we want to do is sell to everyone to
Yes.
maximize the revenue.
Mhm.
So why don't we just, and what we're only really doing is selling to one person drawn from this distribution. If
So-
we're just selling to a single buyer who shows up drawn from this distribution, right? So why don't we just post the price that's the bottom of the distribution? Why doesn't this meet our privacy constraint?
Right.
Just posted price, we don't have to exchange any messages
Yep.
with our buyer.
Yeah, so that's the case where kappa is 0. That's the outcome where you impose full privacy.
And it's
But
also
with no
optional
privacy,
subject
it's not optimal because there's quantity. It's not the single unit case that you might have in mind. In the single unit case, where it's indivisible, there's only two possibilities. Either you sell or don't sell. We're considering a case where there's quantity offered to the buyer. So different buyer types are going to get different quantities in the standard equilibrium.
What do you mean by quantity, like an ex ante constraint on how much you can
No,
sell?
no, no. It's just you demand a certain good, a certain amount, right?
They're like K unit? What do you mean by quantity?
Okay, you can think of K units, but the seller has an increasing cost of production.
I see, so the production costs.
Right. You can think of it that way.
The requirement about the virtual values has nothing to do with the costs, but is just on the demand of the buyers? Is that?
That's right. That's right. Yeah. So in the standard equilibrium, everybody's going to get offered some positive quantity, but that's going to depend some units, but the exact unit number is going to depend on the type.
So the difficulty really has to do with balancing the cost and the quantity.
Sure. Yeah. So that's one way you can think about it. Yes. So to illustrate at least the solution in the uniform distribution case, I'm drawing here the maximum privacy constraint profit for the case of uniform prior distributions that are uniform on 1, 2. So what's interesting, well, the first thing to note is that as we relax the privacy constraint, that is, as we increase kappa, profit always increases. That's not surprising at all. What's a little surprising is that it has these kinks where the curve turns from convex to being concave. So where these kinks are represent the point at which a new interval is added to the optimal mechanism. Recall from the characterization that we said all but one intervals are long, but the last one is short. But we didn't say how many intervals are there. It turns out that the number of intervals involved will increase as kappa increases at these discrete points indicated by the kink. And so in between these kink points, the profit turns out to be convex as we relax the privacy constraint, but at those kink points, the profit change is concave. So finally, we show some results regarding consumer surplus and total welfare in this model. Something to note is buyer surplus is, well, as you can imagine, in contrast to seller profit, buyer surplus is going to be maximized with full privacy. That is the case with a posted price. But under assumptions on the density function, the opposite extreme with no privacy is going to maximize the total welfare. So you can see there's a trade-off between allocation efficiency and trying to maximize buyer surplus per se. So just to quickly recap, we studied the implications of a Bayesian privacy measure, and the main characterization is that the principal will offer a coarse menu in the form of interval partitions. Now, a couple of questions to think about for the future include the actual implementation regarding, in particular, where does the prior come from? And secondly, we haven't really touched upon the issue of multiple agents and how to aggregate the privacy loss across these agents. And then lastly, we focused on static mechanisms, but if you think about the distinction between first price auctions and descending auctions, you will quickly realize that dynamic auctions can save on privacy. So there's much left to do in that direction as well. But that concludes my talk, and thank you.
Time for questions?
So this is very risky what I do, because I will immediately admit that I did not follow all the algebra. But I'm very interested in the assumptions that are there. So I have the feeling that the result is also an assumption. To that extent that you're saying more information about this particular buyer will raise the profit, less information will lower the profit. This means that privacy is a cost to the seller. Now, I think these are assumptions in many ways, because it depends on so many different factors. But if you take that outcome as, for instance, a policy, then you're incentivizing sellers to see privacy as a cost function. It also means that you do not see privacy as an interactional or relational something. I can imagine that if buyers and sellers are in connection with each other, that a lot of the assumptions that return in the outcome are not valid anymore. So I'm a little concerned that the beginning points and the end points are, for a number of reasons, problematic because of the incentives that are there in the end situation and the assumptions in the beginning. That the algebra and reasoning is completely correct. I have to assume that as well. So for me then the question is, by thinking so cleanly straightforward, do we lose sight of what matters? And could somebody who is much better in computer science than me make that argument in a way that is articulate for a computer scientist? I can immediately understand all the reasons to say that this is bullshit, but I'm looking for a charitable interpretation. Because I'm afraid that privacy is here defined in such a way that this will always be the outcome. And that's maybe not what we're looking for, but I'm trying to ask a question. So
Sure.
very
Yeah.
curious.
Thanks for the question. I think it's as with almost all models, the results are more or less driven by the assumptions. So it's fair common to think more deeply about whether the assumptions make sense. I mean, what we have in mind is situations like where this private data is like age information or health information, where certain firms can use to maybe to provide better targeted services and make profits, but the government may be worried that the firm is going to get too much information without any constraints. So that's the perspective we're taking. Obviously, it will depend on the application, and I'm definitely not saying that this is the the only model to think about privacy or anything like that. But at least in some applications, we hope that this will be provide a useful framework.
So maybe just one question. Since you're coming into a semester-long program where many of us have spent a lot of time thinking about differential privacy, maybe you could do a bit to more specifically say why you wanted to formulate a different notion of privacy and the crucial way that you see your measure differs from differential privacy.
Sure. Well, I guess the first main distinction is that differential privacy wouldn't really have any bite in the case of a single agent. In the sense that, at least the way I understand it is differential privacy requires the outcome to be not influenced by changing one particular person's report, holding other person's reports fixed. At least for single agent case, that would not have, much impact. But I think the so that gets to the actual application, which is if we're thinking about regulating firms from collecting data from individuals and in a profit maximizing way, then a lot of these applications are indeed with single agents, like selling house insurance, for example. And so, at least we think this is one step forward toward modeling privacy that is missing from the differential privacy framework.
So I like your shift of focus to the regulator. Two quick questions. One is, do we have any reasons to think we have a benevolent regulator, or do we? What does a regulator need to know in order to make sure that that externalities are checked? And related to that, in one of your slides you said that total welfare will increase to the extent that the price is zero.
So I said that total welfare would be maximized at no privacy. Yes.
No privacy.
So the trade-off, there could potentially be a trade-off.
Right. So I wonder, that goes back to the notion of assumption. Again, to the extent that there could be externalities, so you have two agents and that's it. But perhaps you can answer, well, as soon as we have more than two agents, then that cannot be true, right? Because the whole point is that if you put a network, if we're connected through a web, then the privacy of those two externalizes negatively on others, then the regulator should say, well, clearly we have welfare concerns.
Right. So I understand that comment, and well, we don't have any more concrete results in the multi-agent case. And especially, we haven't really modeled the actionality of one's privacy on other people's welfare. So that's I don't have any of a complete answer to your question. But I think at least this result per se is to at least say that when the regulator, let's say this kappa can be chosen by the regulator, then at least this result would show that in the environments where the model fits or roughly fits, the regulator should think about whether constraining privacy will hurt allocation efficiency by so much that maybe the regulator doesn't want to do that. But of course, there's a separate question of whether the regulator is benevolent or not. And so I think that in that regard, differential privacy is a really good metric because it doesn't matter which person's sort of perspective we're taking, right? Here, we're taking the perspective of a regulator, and obviously, for the model, we have to assume he's benevolent. But again, there's a separate question of even if the regulator is benevolent, can he ensure that the seller truthfully reports? So I think there are lots of open questions to be answered in this space, either in the differential privacy framework or along our framework.
All right. Let's thank Xiaosheng again.